Hey everyone, in this video we are going to learn how to find the domain and range of a function. These two concepts are really important as we're going to define them for every function that we study throughout this course. And beyond this course, we always talk about the domain and range of a function. So building into our definition, answer the following questions based on the set of ordered pairs below. The set of ordered pairs, we have -1, 3, 2, 4, 3, -1, and 5, 0. First question, is the relation a function? So does every input map to only one output? Our inputs are -1, 2, 3, and 5. So each input is unique. It only happens once, and each input maps to only one output, since none are repeated. So is the relation a function? Yes. And we'll write the definition just as a good reminder. Every input maps to only one output. Perfect. So what is the set of inputs? Well, the set of inputs are the values that we've underlined in blue. To write that set of inputs, we're going to use a curly bracket, just like we use for the set of ordered pairs, and we're going to list the inputs from least to greatest. Now, conveniently for us, it already is in that order. So -1 is the lowest, 2, 3, and 5. So that is our set of inputs. What is the set of outputs? So that's the value that each input maps to. So we have 3, 4, -1, and 0. So our set of outputs from least to greatest. The lowest output is -1, then we have 0, 3, and 4. So we have a set of ordered pairs that's a function. We've defined the set of inputs, and we've defined the set of outputs. The set of inputs has a special name. That name is the domain of a function. Okay, so the set of inputs is the domain of a function. And the set of outputs has a special name. That's the range of a function. So here we have the range of this particular function. Defining these, domain is the set of all input values, or the x coordinates, if we're given a point, and the range is the set of all output values, or the y coordinates, if we're given a point. Now that we understand what the domain and range is, let's define these two concepts for as many functions as we can get to. First up, state the domain and range of the following functions, and they've given us a set of ordered pairs. Nice part, they've already told us it is a function, although it doesn't have to be to find the domain and range. The domain of our first function, the set of inputs, so we'll underline these in blue again. So -4, -2, 0, 2, and 4. So we'll list the set of inputs from least to greatest. So -4, -2, 0, 2, and 4. The range of this function is the set of outputs, so the values that every input maps to. So we'll underline these with green and with a squiggled line. Each y coordinate is an output. So we have -2, -1, 0, 1, and 2 as the outputs of this function. And again, nice enough for us, it's already in least to greatest order. -2, -1, 0, 1, and 2. So there we have the domain and range of this particular function. Moving to our next example, the set of ordered pairs 1, 5, 2, 5, 3, 5, and 4, 5. Our domain is the set of all inputs. Those are the x values of each point. So we have 1, 2, 3, and 4. 1, 2, 3, and 4. That's our set of inputs. The range is the set of outputs. So our y coordinates in each ordered pair. So looking at this function, every output is 5. So our range is only going to have one number in it, and that's the number 5. Notice we don't write it multiple times. we had 5 as an output 4 times, right? We have 4 different ordered pairs. We only include the value in the range once. Okay, so if it happened 2 times, 3 times, 4 times, we'd only include that value once. And as a reminder, we always want to write the domain and range from least to greatest. Now, this brings us to an important point. If we compare the number of numbers or elements in the domain to the number of elements in the range, we notice the domain has more numbers in it, right? And that's because each number in this domain maps to the same value in the range. Now, I want you to put your thinking hat on. Could that be switched? Meaning, could we have less numbers in the domain than we have in the range? And to get you thinking in the right direction, think about what the definition of a function is. Every input has to map to only one output. So if we follow that definition, the answer to my question, can that trait be switched? Can the domain have less numbers than the range in a function, right? That's a key. In a function, the answer is no, right? If we only had 4 numbers here and we had, let's say, 10 numbers in the range, that means that the input values would have to map to more than one output, right? The only way 4 numbers would go to 10 numbers is for some of these numbers to repeat and have different outputs. Okay, so that's just a thinking question, not really going to affect finding the domain and range of a function, but I think it's important to notice the relationship between the domain and range and what potential outcomes we could have so that we understand if our answers make sense or not. Now, what happens when we're asked to find the domain and range off a graph? Well, that makes it a little harder because it's not just a list of values, right? We don't have a set of ordered pairs that we can just look at the x-coordinate and the y-coordinate, right? Even more challenging than that, technically, this graph is graphed just on this piece from 0 to 4 on the x-axis, but think about how many x values go from 0 to 4. If we wanted to try to list them out individually, we would never be done. Right? There's an infinite number of values from 0 to 4. So to write them in a list, like we had been doing on the last slides, we'd have a pretty tough time. So we have a solution to that. For continuous sections of a graph, we can express the domain and range as either inequalities, interval notation, or set builder notation. This last one, set builder notation, is the only one we're not familiar with, and we'll go over it after we do inequalities and interval notation. So what is the domain and range going to look like as an inequality? Okay, so we have domain and we have range. So remember, the domain is the set of all inputs, the x-coordinates. So we want to write an inequality that represent what our x-coordinates can be between. So this graph starts at the point 0, 7, and as we move left to right, plotting our points and connecting them to draw our graph, we end at the point 4, 7. So the lowest x value on our graph is 0, the highest x value is 4, and x can be any value in between those two. So let's express that as an inequality. So 0 is less than or equal to x, which is less than or equal to 4. Okay, so we move left to right in writing our domain. Our range, we want to go from least to greatest, the same way that we listed the values out in the previous examples. So we're going to start at the bottom of our graph and work our way up. So the lowest point that I see on our graph is the point 2, -1. So the lowest y value is -1, and as we work our way up the graph, the highest y value that we have on the graph is 7. So that means the lowest y value is -1, the highest is 7. So -1 is less than or equal to y is less than or equal to 7. Important to make that distinction with a y when we're talking about the range, because the range describes the set of all outputs, or the y-coordinates of each point. Okay, so we have to be careful with our variables. That's a common mistake that I see students make. Now in interval notation, well, we're just going to take our inequalities that we've written and turn them into interval notation. So our domain, the interval goes from 0 to 4, and we have equality. It's equal to 0 and it's equal to 4, the x values that is. So we're going to use brackets then. The range, -1 to 7, and it's equal to -1, also equal to 7, so we'll use brackets as well. It's a little bit more condensed when we're writing it in interval notation. So now the new one, set builder notation. Basically think of this as a more formal way to write an inequality. So the domain, expressed in set builder notation, is going to basically put together the curly brackets that we've been using in the previous examples with an inequality. So it's going to look like this. Curly bracket, x with a straight line, and then we're going to include the inequality 0 is less than or equal to x, which is less than or equal to 4. Now the way we read this is the domain are all x values such that 0 is less than or equal to x, which is less than or equal to 4. So this straight line we read out loud as such that. So using this notation to express the range, curly bracket, now the range is the y value, so y such that -1 is less than or equal to y, which is less than or equal to 7. Now the nice part about set builder notation is it's a more formal notation and it allows us to include more information if we need it. Let's say we only had x values between 0 and 4 where the x values were integers. We could write x such that 0 is less than or equal to x, which is less than or equal to 4, comma, x is an integer. So we can include more information when we're using set builder notation. So that's one of the benefits and why we would create this notation, even though in this example it looks almost identical to our inequalities. Now let's practice this. State the domain and range of the following functions using both inequalities and set builder notation. So we'll take this example on the left, so our domain and range, let's write them as inequalities first. So domain is the set of all inputs, the x values. So on the left, I see the point 0, 3, and all the way on the right, 8, 3. So it looks to me that x goes from 0 to 8, moving from left to right on the graph. So 0 is less than or equal to x, which is less than or equal to 8. Now for the range, we want to go from the bottom to the top, work our way up the graph. So there's a few points that are the lowest points on the graph. So we'll just look at one of them. So that's roughly 1.5, 2. We're not as concerned about the x value, so I'm okay with estimating that. And then here, up at the highest, looks to be 2.5, 4. So what's the lowest y value? The lowest y value is 2. The largest y value is 4. So y goes from 2, so 2 is less than or equal to y, which is less than or equal to 4. So now writing it in set builder notation, we'd have x such that 0 is less than or equal to x, which is less than or equal to 8. And then for the range, we'd have y such that 2 is less than or equal to y, which is less than or equal to 4. Okay, so it's nice to do inequalities in set builder notation on the same example because of their similarities. On the example on the right, this is a kind of weird looking graph. It's jumping all around, so we have to really be careful with defining our domain and our range. So our domain, well, working from the left, x is -3, right? That's the point -3, 4. And all the way to the right, it's 3, 3 as our point. But now the question is that x equals -1 and x equals 1, are those going to be included in the domain? And the reason there's a question is because there's this open point on each part of the graph. Now, there's also a closed point at each of those x values, so we do have an output for both -1 and +1 when we input it into this function. So then we're going to work our way from left to right, from -3 all the way to 3. And we don't have to stop. The domain is -3 is less than or equal to x, which is less than or equal to 3. Again, the reason we don't have to break it up into smaller pieces is at -1 and at +1, those inputs do give us outputs on our graph. Now the range, not going to be able to express the range as an inequality. The lowest y value is 2, the largest y value is 4, but we don't hit every value in between. The only outputs are 2, 3, and 4. So if we can list out the range, if it's finite, there's only a few to list out, we're going to do it like those previous examples with the set of ordered pairs. So our range, we're going to list out the values 2, 3, and 4. And even though they said to do this using inequalities, since we cannot do that, we revert to just listing out the values in the range. So now in set builder notation, the domain x such that -3 is less than or equal to x, which is less than or equal to 3. And for the range, y such that y equals 2, 3, or 4. Or we could literally just write it the same way we did up above. Both of these would be acceptable as set builder notation. Another advantage of the set builder notation, we can just list out values if we need to. 2 more graphs, but now we're going to state the domain and range using interval notation. So domain and range. Okay, so for this graph, there's arrows, meaning it goes infinitely in both directions. Well, that means all the way to the left, if I'm looking at the x values, the lowest x value would be -infinity. And as I work my way to the right, the highest x value would be +infinity. So our domain is going to be parentheses -infinity to +infinity. Or as we refer to it, all real numbers. Now what about the range? Well, this arrow is going to keep going. It's going to go slowly, but technically it just keeps going all the way down and down and down and all the way down. So the lowest y value that we're going to get as an output for this function is going to be -infinity. Again, a little weird to wrap our head around because it goes down slowly, but eventually it's going to get there. And the largest y value, if we follow this side of the function up infinitely, it's going to get to +infinity. So our range is going to be -infinity to infinity. So this is a nice example to use interval notation because we have the ability to write out this interval nicely. And remember, this is all real numbers. So the domain and range of this particular function is all real numbers. Turning our attention now to the next example. So we have a weird looking graph again, and we need to define the domain and the range in interval notation. So the domain, the lowest x value is -4. The largest x value is 3. Notice I'm not writing the points out now, trying to do it without that. Now the question is, at -1, do we include that in our interval, or do we have to do it as -4 to 1, -1, and then -1 to 3, so 2 separate intervals? Well, at -1, we do have an output on this function, so -1 counts as an input, so we would include it as we're going from -4 to 3, so we can just write one interval, -4, 3, and we'll have a set of brackets around each side. Now, could you break it up? Yeah, you could have written -4, -1 with a bracket and a parentheses, and then union -1 to 3 with a bracket on both sides. That would be correct as well. Now the range, we're going from the lowest y value to the highest y value, listing out all potential outputs. So the lowest y value is -4. The largest y value is 5. And we have equality at both of those y values. Now the question about this gap here, Well, because we have this part of the graph, which covers all of the outputs from 0 to 4, then we include all of it in our interval. Okay, so these two are a little more challenging, got us thinking a little bit more, but hopefully you can follow the reasoning as to why the domain and range for each function is what we got. What is the range of the function f of x equals 3x squared minus x plus 4 if the domain is the set -1, 0, and 1? So they've given us our set of inputs, they've given us our function defined algebraically. We need to figure out the set of outputs, or the range. So we can do that by evaluating the function at each of our inputs. So we'll start by evaluating f of -1. So substituting -1 in for each x in the function, we have 3 times -1 squared minus -1 plus 4. So -1 quantity squared is +1, so we have 3 times 1. Subtracting a -1 becomes +1 plus 4. 3 times 1 is 3, plus 1 is 4, plus 4 is 8. So if we input -1, we output +8. Next, we'll evaluate f of 0. So substituting 0 in for each x, we have 3 times 0 squared minus 0 plus 4. So we have 3 times 0 minus 0 plus 4. So we have 0 minus 0, which is 0, plus 4 is 4. So if we input 0, our output is 4. And last, we'll evaluate f of 1. So substituting 1 in for each x, 3 times 1 squared minus 1 plus 4. We have 3 times 1 minus 1 plus 4. So we have 3 minus 1, which is 2, plus 4 is 6. So our range from least to greatest is 4, 6, 8. So we talked a lot about the domain and range in this video. We looked at a set of ordered pairs. We looked at from a graph, right? We defined it with inequalities, with interval notation and step builder notation. And then we practice evaluating functions in this example. Only thing we haven't talked about yet is graphing a function on a restricted domain, which will be in the next video. So go practice these ideas and concepts and rewatch any part of the video to go over the domain and range if you need. Click the Amazon link down below for my algebra workbook so you can practice on your own. Give the video a like, and before you go, click that subscribe button so you can see more videos just like this. Thanks for watching.